Hi class, today we're going to cover Anova. I'm going to show you what it is and how to do it on your TI-8384 calculator. So let's get started. So Anova is analysis of variance, and it basically tests the null hypothesis HO is whether the means of different populations are exactly the same. And the alternative is that they're not all the same. We're going to use Anova and put our data into lists L1, L2, L3, continue on how many you have, and use the function Anova, and it will return a p-value basically, and then we can either accept HO or reject HO, or either reject HO or not reject HO. Basically, our analysis of variance will have a distribution that's called an F distribution, and it has some degrees of freedom with the numerator and a denominator. And it looks like a chi-squared distribution, and here's some degrees of freedom or sample size of size 4, and 4 is this color. Basically looks like a chi-squared distribution. Analysis of variance, we have an F statistic. It is a variance between samples divided by a variance within samples. And so we have degrees of freedom of the numerator is, if we have k categories, we'll have k minus 1 degrees of freedom. And the degrees of freedom of the denominator is k times n minus 1, where n is the number of samples in each category. So let me give you an idea of what analysis of variance is. If we took samples from a population, say the true population mean is mu1, and we have some variance within that, and then if there was a mu2, a population of mu2, and say the variance, values go from say here to here in general, and a third population with mu3, and again the variance is maybe looking kind of like that, our variables. Then our variance between samples is going to be much larger than the variance within samples, and we'll be able to say that those three means are actually different. But if the means, if the population mean 1 was here, and mean 2 was here, and mean 3 was here, and each one had a lot of variation, say this one had variation like this, and this one had variation like that, then the variance between samples is relatively small compared to the variance within samples, and so that the ratio won't be very large, and we won't be able to determine whether the means are actually different within our samples. But if the variation within samples is much less than the variation between samples, then we can say that there's a difference between the means. And that's basically what analysis of variance is doing. So let's do an example. Jeff Parent is a statistics instructor who participates in triathlons. Listed below are times in minutes and seconds that he recorded while doing a bicycle ride for 5 laps, each on a 3-mile loop. So let's use a 0.05 significance level to test the claim that it takes the same time to ride each of these miles. Okay, so we have mile 1, mile 2, and mile 3. Those are the 3-mile loops. And he did each one 5 times. And can we say that they're different, and that one might have a hill and it would take him longer? So does any of these look like they could take longer? And maybe mile 3 in general takes a little bit longer than the others, but we'll see if that's statistically significantly different. All right, so let's do that. All right, well, HO is that mu1 is equal to mu2, which is equal to mu3. And HA is that they're not all equal. Okay, so we get an F statistic, and we'll get a p-value. And let's see what our p-value is equal to. How do we get our p-value? Well, let's bring in our calculator. And let's go into stats and edit. So let's put the data in L1, L2, and L3. So we have 3 minutes and 15 seconds. So let's convert that to seconds. 3 minutes is 60 seconds per minute. So that's 180. So this will be 195. So we'll put 195 in there. This one will be 180 plus, so that one will be 204. And this one is 203, 202, and 201. Okay, this one will be 190, 199, 202, 201, 197, and 199. They don't look too different. But now this one, that's 180 plus 30. So that's 180 plus 30, 121. So 1, 2, 2, 1, and a 4. And this one's 2, 1, and a 1. This one is 20, 209. This one is 213. And this one is 209. It's always good to make sure that you have the data correct in there. Looks like it is. So very simply, we now go to stats and tests. We go up from the bottom. We have Anova at the end. We say enter. And then we just say L1. So second L1, comma, second L2, comma, and second L3, close parentheses, drum roll, and we get a F statistic, which is 27.9, but that doesn't mean much to us, but a p-value does, and you don't have to worry about all this other stuff. P-value is 3.0 times 10 to the minus 5. Okay. So we'll go 3.0 times 10 to the minus 5. Of course, that's less than alpha, which is 0.05. So that's equal to point. We move that over 4000003. Certainly less than alpha, so we reject HO. Reject HO. And conclude that one of the miles does appear to have a hill, or that all the miles, it takes longer to do one of the miles than the others. And it looks like this one takes longer, and so therefore it probably has a hill. All right, so that's an analysis of variance. They were not all equal. Let's do one more example. And this comes from actually the history of it does come from agriculture. Okay, so tree weights, right? The weights of poplar trees were obtained from trees planted in a rich and moist region. Okay, and basically they were given different treatments. They were given either no treatment, a fertilizer, irrigation, or fertilizer and irrigation. And we can ask, did any of these have an effect? And so the null hypothesis, HO, is that mu1 was equal to mu2, which is equal to mu3, which is equal to mu4. None of the treatments had an effect. Or HA, not all equal. Okay, that means some of the treatments had an effect. And certainly this one looks larger, but is it statistically significantly different from the others? So let's plug that stuff in. So let's put our data in. We got It really doesn't take too long to put this data in. Okay, all our data is in there correctly now. So we'll go to Stats, Tests, Anova, right? Now there's our sample result, and we want to see if those, sample results, could come from a situation where all the means are equal. Are they within sampling chance? There's always variability. Is it within sampling chance, or is it really clear that the means are not equal? And we can infer the alternative. So we put in our list, second L1, and second L4, close the parentheses, drum roll. What's our p-value? F-stat is much smaller. Our p-value is not as small as before, but still small. 0.006 that will round up to, less than alpha, so we do have statistical significance. So we get our p-value was equal to 0.006. That is less than alpha of 0.05, so reject HO. And conclude that that the means are not equal. So there does appear to be a treatment that is most effective, and that's fertilizer and irrigation looks about the best. They're certainly different. Okay, well, I hope this video was useful for your learning and that you enjoyed it. And cheers.